Hi everyone. We are about to get into second derivatives in graphs a little bit more. So remember that second derivatives tell us about the concavity of the original function. So if the second derivative of f is positive, that tells us that f prime, okay, so this is a single derivative. The derivative of f prime is positive. That tells us that f prime is increasing. And if f prime is increasing, that means my slopes are getting bigger, and that tells me that f is concave up. So remember, there's this how many steps. If you're 2 steps apart, 2 derivatives apart, then it's concavity, how's the bend? And if you're 1 step apart, it doesn't matter which spot, then it's slopes. So positive derivative of f prime tells us positive slopes of f prime. Positive second derivative tells us concave up. And then if the second derivative is negative, that tells us that the first derivative is decreasing. So slopes are getting smaller and smaller and smaller. So there's a couple of things that could appear to be, this one is usually the easy one, which means the function is concave down. What else is on my definition here before we get into second derivative tests? Okay, so if the function is continuous at x equals p and changes concavity at that same x value, then f double prime, okay, so if it changes concavity, that means that f double prime switches either from positive to negative or negative to positive, and we will say that f double prime is 0, although that could happen when f double prime does not exist. That's not really what I'm going for here, so we're just going to ignore that fact temporarily. If f double prime doesn't exist, then we just don't give that point a special name. Actually, if there's a vertical, it's possible, so we'll just put them both. And f prime, okay, so if the second derivative is 0, that means f prime has a flat spot, and in particular, we're saying f double prime changes concavity, so it either goes positive, negative, or negative, positive, which means f prime was either increasing then decreasing or decreasing and then increasing. So this is actually, I think, really interesting. The points where concavity changes are local maxes or mins of the first derivative. So if we're, okay, let me just finish this because I keep stumbling over my words because I'm trying not to use this last one yet. And if we want to talk about what's going on the function, a point where the function changes concavity is called an inflection point. Okay, so basically, point. What I kept trying to say and stumbling over is that if you're looking for an inflection point or talking about an inflection point of your function, that's going to happen when the function changes bend, when the first derivative has a max or a min, or when the second derivative is 0 or undefined. Those are the things that we're looking for. Okay, so just to make sure, because this concavity stuff is usually the trickiest for people, so just to make sure we're kind of good with the general stuff going on here, pick out some colors that work. Okay, this graph is just going to be something we look at to identify some critical numbers, inflection points, stuff like that. So here's our function f of x. We want to figure out what the critical numbers are. So remember that critical numbers happen when the derivative is 0 or undefined. So this function has flat spots. Where would I say that flat spot is? Right about there. At 3 different points. So it looks like there are critical numbers at x equals 2, at x equals 5 1/4, and at x equals 8 1/2. Those appear to be the critical numbers. We are also supposed to try and estimate where we have inflection points. So inflection points are where the bend changes. So I would say, looking at this graph, it looks like I'm for sure concave down through here and also through here. So that's for sure concave down. And then I think it's for sure concave up all through here and I am trying to figure out where it switches. So I think there should definitely be an inflection point somewhere in the middle here. We'll just make it easy and say it's at 3.5. So we do some estimating. Let me think about this one. Down, up. I actually think it's maybe right around, do I think it's there? I'm going to say it's 7.25, but there's definitely some estimation happening. And then it's kind of hard to say on the end. It could have switched. It looks to me like this is still kind of on that same bend, and this is still potentially kind of on that same bend. I can't tell for sure that it's switched yet, so I'm just not going to worry about it. But definitely, when x is about 3.5 and 7.25, it looks like I have inflection points. So the bend is changing. So don't confuse your critical values and your inflection points. People tend to do that. Okay, identify which critical numbers are local maximums and minimums. What can you say about the second derivative at the maximums and the minimums? So we have a max, and a min. Notice that at the maximum, this function it's a flat spot, so the first derivative is 0, but it's definitely bending down below that tangent line. So f double prime is negative. And at this one as well, it's definitely bending down, so f double prime is negative. And then notice at the minimum, it's definitely bending up above that tangent line, so this is an f double prime is positive. So this isn't a very big pattern, but what it looks like we're seeing is that at the critical value, if the second derivative is negative, then it's a max, and if the second derivative is positive, it's a min. And this is what leads to our second derivative test. So the second derivative test is a little bit limited in its application. It doesn't work on absolutely every scenario. And the restriction is this part right here. Actually, there's a little bit more to it than just that part, but that's the first thing. So it only works on flat spots. It doesn't work on corners. On corners, the bend can be doing all sorts of weird stuff. So if your function has a flat spot at x equals c, then you can check its second derivative. So if there's a flat spot and the function is concave up, that has to be a minimum. If there's a flat spot and the function is concave down, that has to be a maximum. The other spot that the second derivative test gets slightly tricky is if there's a flat spot and the second derivative is also 0, the test just doesn't work in that case. What that means, like y equals x to the fourth is a good example. Y equals x to the fourth absolutely has a minimum at the origin. This is kind of what it looks like. So definitely there's a minimum at 0, 0. But if you try a second derivative test, y prime is 4x cubed, so y double prime is 12x squared. So the critical number is at x equals 0, and when you plug it in to the second derivative, you get 0. And what's happening is that this fourth degree power function is so flat at the bottom that not only does it read as having a horizontal tangent line right at that point 0, 0, it also reads as not having any bend at all. So if you move a little left or right, then all of a sudden you can find concave up, but right at that point you can't. So if this happens, if you have a flat spot and the second derivative is 0, you just have to go back to your first derivative test. Okay, so I see a little note to myself. I think I will do this really quickly. I want to look back. I don't think I need to look back at number 3. It's kind of just a mess, but I will look back really quick at number 2 if I can find it. Oh, found it. Okay. So just to see this in action, this isn't anything terribly exciting, but this is a great example of when the second derivative test is really nice. So to do a second derivative test, we'd have to do this little bit of work. We'd have to find a first derivative, and then we'd skip all of this. Oh, that's not entirely true. We'd have to do all of this work because we need to know what our critical numbers are. So we say we have critical values at x equals 2 or -1. And then what we would do is we'd say f double prime is equal to 12x minus 6. And all I need to do, I don't need this whole sign chart. All I need to do is figure out at these two flat spots, because they are flat spots. So I'm thinking x equals, again, I don't know why that's got a y-axis, 2 or -1. There's a flat spot at each of those. And the second derivative tells me that at x equals 2, I have 24 minus 6, which is 18. The function is, that was x equals 2, concave up, which means there's definitely a minimum there. And at x equals -1, I get -12 minus 6, which is -18. So the function is definitely concave down, which means I have a maximum. So that's how it would work. So notice the difference between these two. This gets a little confusing, and when we add inflection points to the mix, it kind of scrambles it even more. If you're trying to use a first derivative test, that involves making a sign chart, finding your critical values, and then testing slopes nearby your critical values, between them, right? If you're trying to do a second derivative test, that involves finding your critical values and then checking exactly at each critical value, not nearby, for the concavity. So start to really think carefully about when you're checking nearby points versus the critical values. That can be confusing. All right, thanks for watching.